In section 9 of this course, we look at the method of Ragazzini, and it's also known as model reference control. The idea is very simple. We construct a controller C of Z, so here we're doing direct digital design, so we are going to work on the basis of a process P of Z that includes the zero order hold mechanism, so we need the zero order hold equivalent description of the system. So the idea is to control a controller in such a way that the desired closed loop transfer function is a desired transfer function. Okay, so this is something that you can design yourself. Remember that the overall closed loop transfer function, and it's the closed loop transfer function from reference or set point to output, is the complementary sensitivity function. So this will yield a design formula that is as follows. So we can obtain it very easily. So this is our desired transfer function, and we know that it is P of Z C of Z over 1 plus P of Z C of Z. We can multiply by the denominator, so we have T desired Z plus P C T desired is equal to P times C. We take this one on the other side and we put PC in front, so we have T desired is PC 1 minus T desired Z, right? And what we're looking for is C, so we can divide by 1 minus T desired and by P, and this is how we obtain this formula, right? So the idea is very simple. You choose a desired closed loop transfer function and you're given the process, and by this design formula you obtain the controller. But of course it's a bit more difficult than that, because you can already see here that if you look at the loop gain P times this controller that we designed, you can see that the process dynamics are cancelled. Okay, so we have to make sure that everything goes right, because what could happen is that we have unstable pole zero cancellations, right? And this would go against internal stability. So the idea now is to kind of discover and implement constraints on this desired transfer function so that we do not ask for the impossible. Well, an obvious constraint is that the controller must be causal, so it must have at least as many poles as zeros and therefore no time advance. The controller must be well behaved when z tends to infinity, and it does not have therefore any pole at infinity. Let us take a counter example. So our controller is C of Z, and we have here z squared plus 0.5 over z plus 0.7. Obviously it has more zeros than poles, and you can see that when z tends to infinity, well, this will tend to infinity, so we have also a pole at infinity. So we'll show now that indeed this controller is non-causal. So you can rewrite this by dividing by z at the numerator and denominator as z plus 0.5 z minus 1, 1 plus 0.7 z minus 1. So what we'll have is 1 plus 0.7 z minus 1 mv z is z plus 0.5 z minus 1 e of z. Then what we'll do is take the inverse z transform. We'll have here mv at sample instant k plus 0.7 mvk minus 1, so we'll take it on the other side, so we'll have minus 0.7 mvk minus 1 here, minus 1 plus, and here's the problem, the error at sample instant k plus 1 plus 0.5 the error at sample instant k minus 1. So you can see here that this controller is not causal because the output of the controller at sampling instant k depends on the error in the future at sample instant k plus 1. This is not something that you can implement on a processor, so therefore you must have at least as many poles as zeros, and the controller must be well behaved when z tends to infinity, so it cannot have poles at infinity. So we want our controller to be causal, and this controller is coming from a design with the method of Ragazzini or with model reference control. So it's 1 over p times the desired transfer function over 1 minus the desired transfer function. So we want this one to be causal. So if we have, for instance, a 0 at infinity for this process, let us take a process here that has a 0 at infinity. This process here has a 0 at infinity. If you put z and you let it tend to infinity, this will tend to 0. So z tending to infinity is indeed a 0 of the process. But here you have it as 1 over p of z, so this will give here a pole at infinity, which we have seen could be problematic, right? Except if we cancel it in the desired transfer function. And how can we cancel it? By putting, of course, a 0 at infinity in the desired transfer function. So we have the following constraints on the desired transfer function for C to be causal. It is that, well, the number of zeros at infinity in the desired transfer function must be at least, well, the number of zeros at infinity in the process. Well, you can see here that the number of zeros at infinity, so here we have 1 0 at infinity, is also the delay of the system. You can rewrite this transfer function here by dividing by z square at the numerator and denominator, and we have here z minus 1 plus alpha z minus 2, 1 plus beta z minus 1, right? And this is here y of z over x of z. So what we have here is y of z times 1 plus beta z minus 1 is equal to z minus 1 plus alpha z minus 2 x of z. So if you take the inverse z transform, you can see here that inverse z transform, that y of k, we'll take this one on the other side, is equal to minus beta y of k minus 1 plus x of k minus 1 plus alpha x of k minus 2. So the delay in the system is a delay of 1. So this constraint that we had here on the number of zeros at infinity can be translated in terms of time delays. So what we say here is that the delay of the desired transfer function should be larger or equal to the delay of the process. Okay, and in practice what you will do is simply say equal. So if there is a delay in the process, well, it kind of makes sense that the closed loop transfer function should have at least a delay that is the same as that of the process. There is nothing that you can do about a delay, but of course there is no reason why you would take the delay in the desired transfer function higher than that of the process, because this would only delay things. So in practice what you do is to take the delay of the desired transfer function equal to the delay of the process. We have seen a first constraint on the controller, that it must be causal, and this has imposed a constraint on the desired closed loop transfer function, that the delay of this transfer function must be at least that of the process. Remember also that we have in this design the possibility of unstable pole zero cancellations, and these are of course prohibited because they go against internal stability of the closed loop system. So if this comes as a surprise, you should have a look at the section about internal stability. So we assume that we're given a process that can be described as a transfer function, and at the numerator we have a polynomial b of z, and the denominator a polynomial a of z. What we'll do is factor both b of z and a of z in such a way that you have, well, a polynomial that has all the stable poles and zeros. Okay, so the ones that are inside the unit circle and the ones that are outside the unit circle. So for instance, we factor b as b plus as all zeros inside the unit circle, and b minus as zeros outside the unit circle, and we do something similar for the polynomial a of z. Remember that c of z is 1 over p times t desired over 1 minus t desired. So this is here 1 over p of z, where p of z is given over here. And if we look at unstable pole zero cancellations, we have to look at the loop gain, p times c. So if we do not impose anything particular on the desired transfer function, we have a danger of unstable pole zero cancellations over here and over here, right? So this is something that we have to prevent. And how can we prevent this? Well, by an appropriate choice of the desired transfer function over here. So for instance, if we want to prevent that b minus is cancelled by the b minus in the process, what you can do is make sure that b minus is a factor of the numerator of the desired transfer function, so that the desired transfer function is, well, b minus z times something, this is the numerator, and then a denominator. In such a way, in the controller, what we'll have is a cancellation over here. So this b minus will disappear from the controller, and you cannot have any cancellation of the zeros that are unstable in the process. And this is simply because this b minus has disappeared from the controller. Of course, you can do something similar to prevent that these ones, or these zeros over here in the controller, will cancel the unstable poles of the process. We have to make sure that this a minus z is a factor of the numerator of 1 minus t desired z. So we have that, we have to impose that 1 minus t desired z can be written as a minus z, so it's a factor of the numerator divided by something. And in such a way what we'll have is this one here is at the denominator, so we'll have a cancellation of this one and this one. So this a minus will disappear from the controller, and you cannot have any cancellations with the poles of the process. So in summary, this is our process where we have factored b and a in such a way that we have the roots that are stable in the plus component and the ones that are unstable, so outside the unit circle, in the minus component. We are designing a controller using this method of Ragazzini, so we have here 1 over p of z, right? And we want to prevent unstable pole zero cancellations, right? So if CZ is not to cancel the 0 of PZ, right? Which one do we not want to cancel? Well, this one over here, right? Then we have to make sure that this unstable zeros of the process are a factor of the desired transfer function. So the desired transfer function must contain all zeros that are, between quotes, unstable in the process. Because if you rewrite this as b minus z times something divided by something, well, you see that b minus disappears from the controller, and you cannot have an unstable pole zero cancellation in the sense that the unstable zeros of the process are cancelled by the controller. If the controller should not cancel the unstable poles of the process, well, then you have to make sure that these unstable poles are a factor of 1 minus t desired. So 1 minus t desired must contain as zeros all unstable poles of the process p of z. So we must have here that we have a minus z times something divided by something. You can see here that the zeros here in 1 minus t desired are the unstable poles of p of z, and so what will happen is that this one will cancel with this one, so a minus z will completely disappear from the controller design, and you cannot have an unstable pole zero cancellation of these unstable poles of the process over here. Sometimes it is wise to include additional constraints that go further than the ones that we have introduced, even if they are not necessary from a perspective of internal stability. Remember that our controller designed according to this method of Ragazzini looks like, well, 1 over p, and here we'll write it in terms of these polynomials. So this is here 1 over p of z, and then you have t desired 1 minus t desired, right? Well, if you have here zeros that are stable in the sense that they are in the unit circle, but that these zeros are located over here, well, this will lead to problematic behavior of our controller, C of Z. Remember that if you have a 0 in this region, so assume that you have a transfer function 1 over Z minus alpha, okay, and alpha is here in between 0 and -1, so in this region over here, and this Z minus alpha is here a denominator in the controller. This will lead to problematic behavior, because if you take the inverse Z transform of this one, what you'll have is alpha k u of k. But if you look at the behavior of this one, you will have something like this. K is equal to 0, that's 1, right? K is equal to 1, that's something negative. K is equal to 2, something positive. So you can kind of see what will happen. If you have a 0 here in B plus that is located in this region over here, the control energy will be such that you will have this alternating behavior, and this is really not something that is desired. So if you have zeros of the process that are stable, in the sense that are inside the unit circle, but that they are placed over here, well, you should probably make sure that T desired is also written as B plus Z times something divided by a denominator, so that they cancel out from the controller and that you cannot have this design, right? So it's very important to make sure that your controller does not have poles in this region over here. And well, if it's close to the origin, it's not that big a problem, because it will go to 0 very fast. But if these poles of the control are located over here, this will take a long time before this effect disappears. And these are coming from zeros of the process that are located in this region. So if you want to make them disappear, you should make them a factor of T desired. Another obvious constraint on the closed loop desired transfer function is that its static gain must be 1. This is kind of obvious. If we take a unit step input, the steady state should be equal to 1, right? Remember that from the final value theorem, we can obtain that the steady state response is, well, the limit of Z tending to 1 of Z minus 1 times the response Y of Z, and here the response is the unit step response, so it's T desired times the Z transform of U of K, the unit step, right? If you take this limit, you can easily see that this is T desired evaluated in Z is equal to 1, right? And this is equal to 1. So this is the constraint that we have to impose, but this is really saying that the static gain, remember that we obtain the static gain by taking the desired transfer function and evaluating it in Z is equal to 1, and it must be 1, right? So this is an obvious constraint that we should not forget in order to impose a zero steady state error. So we'll now design a controller, a digital controller, for our tutorial process using the method of Ragazzini, right? So this is direct digital design, so we should base our controller design on a zero order hold equivalent description of the process, and we have computed this previously. As you can see here, this slide has been recycled from previous slides in the course. And here A and B can be computed as follows. T is the time constant, it's 10 seconds, and in our case here we'll take TS is equal to 1 second. So what we'll use are, of course, the same specifications: a settling time of 10 seconds, or equivalently a closed loop time constant of 2 seconds, an overshoot of 17%, so a damping ratio of 0.5. So the settling time is 5 over zeta omega n, or equivalently the closed loop time constant is 1 over zeta omega n. With a zeta of 0.5, this yields a natural frequency of 1 radian per second. So the desired continuous time closed loop system has a characteristic polynomial that is given over here. From that you can compute the closed loop poles. It's easy, you'll just have to complete the squares. So s plus zeta omega n squared, so this will produce this one and this one. What you'll have too much is zeta square omega n squared, so you'll have to subtract it. So we'll have plus omega n squared 1 minus zeta squared. So the continuous time poles are minus zeta omega n plus minus j omega n square root of 1 minus zeta square. We are of course interested in the discrete time poles, but they are linked by this relation over here. Remember that z is the exponential of TSS, right? So if you inject that in here, so what you'll have is exponential of minus Ts zeta omega n exponential of plus minus j Ts omega n square root of 1 minus zeta square. So this one you can write it as r0 exponential of plus minus j omega 0. So this is the polar form of the discrete time poles. So you can see here that r0 is exponential of minus Ts zeta omega n. In our case, this will be exponential of minus 0.5 times Ts, and omega 0 is Ts omega n times the square root of minus zeta square. In our case, this will be Ts times the square root of 1 minus a half square. So this will be Ts times the square root of 3 divided by 2. If you're wondering if this is new, well, it's not. It's something that we've seen previously. So here is the computation of the poles. And here we have the computation of the poles in the z domain from the poles in the s domain using this relation. So this is r0 and this is omega 0. Well, we have just seen that we had two discrete poles, right, where r0 is given by this expression and omega 0 is given by this expression. So we can now compute the discrete characteristic polynomial, and it is z minus r0 exponential of j omega 0 times z minus r0 exponential of minus j omega 0. And if you compute this, what you'll have is z squared minus r0 exponential of j omega 0 plus exponential of minus j omega 0 times z times this time. So this is r0 squared, right? And this is 2 times the cosine of omega 0. So this is why we have the following discrete characteristic polynomial with r0 and omega 0 that is given over here. In general, r0 is the exponential of minus omega n zeta ts, and omega 0 is equal to ts times omega n times the square root of minus zeta square. So then you have a direct relation between zeta and omega n and ts, and a relation with r0 and omega 0 over here. So the desired closed loop transfer function is the following one. So you can see here that at the denominator I have this discrete characteristic polynomial, and here I'll have a numerator. And of course, for this numerator we'll have to kind of take into account these constraints that we had imposed on the desired discrete closed loop transfer function in terms of causality of the controller, preventing unstable pole zero cancellations, and also having a static gain that is 1. Well, let us now look at these constraints, but first of all we have to write the description of the system. It's the zero order Holt equivalent that we have found previously. It's z minus 1, a plus b z minus 1, and then we have 1 minus z minus 1 times 1 minus exponential of minus ts over t z minus 1. Okay, so this is the transfer function. So in order to have causality of the controller, well, we see that there is a delay of 1 in the process. Well, we need also a delay of 1 in t desired. This means that we have to take b0 is equal to 0, so that we can write the numerator here as z minus 1 b1 plus b2 z minus 1. We need a zero steady state error, so it means that t desired evaluated in z is equal to 1 is equal to 1, and since b0 is equal to 0, this imposes the following relation, right? So this thing here with z is evaluated in 1 is equal to 1, so this is equivalent to this equation. We see here that z is equal to 1 is an unstable pole of the process. You can see it over here. So it must therefore be a 0 of 1 minus t desired. Okay, t desired, we have it over here. So 1 minus t desired is 1. We'll put everything under the same denominator. The denominator is this one over here. So if we write 1 minus and we put everything on the denominator, with the 1 we'll have z squared minus 2r0 cos omega 0 z plus r0 squared, and then minus the numerator, but b0 is 0, so we'll have minus b1z minus b2. So indeed this is what you have over here, but this unstable pole of the process must be a 0 of 1 minus t desired. So this means that this numerator here, we should be able to factor it as z minus 1 times z minus alpha for some alpha. So this is the constraint on minus t desired. Okay, we had seen that z minus 1, the unstable pole of the process, had to be a 0 of 1 minus t desired. So if you look at the independent terms, this will yield this equation, right? And if you look at the terms in Z, right, equating this one with this one over here will produce B1. If you kind of sum these two, you can see immediately that this is exactly the constraint that we were requesting for T desired and Z is equal to 1 is equal to 1. This is kind of, well, obvious if you look at this, imposing that Z minus 1 is a 0 of 1 minus T desired is really saying that 1 minus T desired evaluated in Z is equal to 1 is equal to 0. Okay, so this is equivalent to imposing T desired in 1 is equal to 1. So here alpha is a parameter that we can use as a degree of freedom. Okay, so we have to keep it in the interval 0 to 1 and smaller than 1, and of course it cannot become larger than 1, otherwise, well, we'll introduce an unstable 0 in T desired, and this will give you this inverse type response. Now we can compute our controller that is obtained using this method of Ragazzini. So it is 1 over P. This is indeed 1 over P. This one over here is T desired, and this one here is 1 minus T desired, and we know here that the numerator can be written like this. There is a factor Z minus 1 in here. So now we can start cancelling out. This one you can cancel out, this one you can cancel out, this one you can cancel out, and this one you can cancel out. And this is now my Ragazzini design, okay, where alpha here between 0 and 1 can be used as a degree of freedom. Notice also that in this Ragazzini design, B1 and B2 are obtained from these equations here. So they also depend on this parameter alpha that can be used as a degree of freedom. So we can now have a look at the Matlab code to generate the responses using this controller designed with the method of Ragazzini. We work in Matlab, so you'll only be able to see what happens at the sampling instance, and you'll not be able to see the inter-sample behavior. Okay, so this is the process that we're tackling, and this is the zero order hold equivalent description. We could have used the command C to D, but here we have used our hand calculations. So what you see over here is the, well, desired closed loop transfer function. It's omega n squared over s squared plus 2 zeta omega n s plus omega n squared. In this case, with omega n is equal to 1 and zeta is equal to 0.5, this is the desired closed loop transfer function, right? So here we compute the controller, right? So these are the poles, and the discrete poles are R0 exponential of plus minus j omega 0. So this is the computation of R0 omega 0. This is our degree of freedom. Here we choose to take alpha is equal to 0.4. You can change this value and see what happens. Remember that B1 and B2 are a function of this parameter degree of freedom alpha, right? And then you can compute the numerator and the denominator of the Ragazzini controller like so. Once you have numerator and denominator, you can compute the transfer function. And now what you can do is compute the closed loop system. This is the relation from R to Y, or from set point to PV. And here we have the relation from R to X, or from set point to manipulated value. And then you can look at the step response. So this is the output closed loop response. In blue, the set point. In cyan, you see the desired closed loop response. Okay, but this is the desired in continuous time, right? And you see here the Ragazzini design. So the closed loop step response with Ts is equal to 1 and alpha is equal to 0.4. This is what you can see in Matlab. Okay, if you want to see the intersample behavior, you should use Simulink. So what we can do is have a look at the intersample behavior, and this is what you see. So you can see here that there is a hidden oscillation, and this is why you should always check intersample behavior. And this is why preferably when you have a digital controller, you should test it in Simulink. So this is the Simulink simulation for this first Ragazzini design. Remember that this is the process, and in front you have to put a zero order hold mechanism. Do not forget to change the sample time. This is really crucial. Here we have the rate transition, right? And here you have the digital controller. So this corresponds to the Ragazzini design number 1. And here again, TS is imported. So if you simulate this, this is how it looks like. And you can see indeed that you have the same results than in Matlab, but on top you have the intersample behavior. And here you can see that there is this hidden oscillation that you cannot see in Matlab, and that is undesired, and it comes from the fact here that this controller output is oscillating between a positive and negative value. And by now you should have found why this is the case. This is because we have in the denominator of the controller a pole that is stable, but it is in the interval -1, 0. Well, when you check your response only in Matlab, you should certainly look at the output of the controller, because by looking at the output of the controller we can suspect that there is a problem. You can see here that the control energy, well, is positive, negative, positive, negative. So there is this alternation of signs from sample to sample, and this is of course clearly not desired. We had here a process with a 0, that is AZ plus B, and here at the denominator we had, well, something like this. This is Z minus 1, and the other one comes from the main time constant T. And what we have done in the controller is, well, cancel this 0. So we have here something with AZ plus B. The problem is that the associated pole of the controller, the associated 0 of the process, is, well, stable, but it's located here in the unit circle. Very close to -1, and this is what is causing this alternation of signs in the control effort. So to avoid this, we should impose that, well, this factor here should be a 0 of t desired. Okay, so the t desired is az plus b, so that we keep it in the numerator in t desired. So in this way we will not find it at the denominator of c of c, right? So we could see that the intersample behavior was much worse than we could expect if we looked only at the discrete response in Matlab. Okay, so the lessons learned. Well, cancelling a stable zero that is located in this region over here is not a good idea, because it will lead to oscillations in the control effort, and this effect will worsen the closer the zero gets to the unit circle. So the closer it gets to z is equal to -1. And of course you always have to check intersample behavior, so use Simulink to do this, as I have shown previously. Well, in this second design we keep our zero over here that is located, well, on the real axis, but on this side over here in the numerator of our desired transfer function. You can see that if you write everything in terms of z minus 1, that you have a delay in the system of 1, which is also precisely the delay of the process. So we have taken the causality constraint into account. What we need to do is to take the constraint on the zero-steady state, right? And this is imposing that the desired transfer function evaluated in z is equal to 1 is 1, so that the static gain is 1. If you impose that, well, this will impose k, and it's easy to compute that this is what you have to choose. Remember that z minus 1 was a pole of the process, so we need it as a 0 of 1 minus t desired, right? This is 1 minus t desired, but this is equivalent to t desired in z is equal to 1 is equal to 1, so this constraint is already satisfied. But nevertheless, it's good to write 1 minus t desired in such a fashion where the numerator is factored as z minus 1 times z minus gamma 1, where we have to determine gamma 1, right? Well, if we compute this, this is what we obtain, and you will see here that if you equate this one and this one, you obtain the value of gamma 1 as shown over here. And you'll be able to show also that this one is equal to this one, and this will come from this relation over here. So now we are ready to write the controller, the digital controller that is coming from this second design using the method of Ragazzini. So the controller for the Ragazzini design is given over here. This is 1 over the process, right? What you have here is t desired, and here we have kept this 0 that's coming from the process. It will cancel out, so you'll not find it in the denominator of the controller, and this is 1 minus t desired that we have rewritten in such a way that you have the z minus 1 as a factor. This one will cancel out with this one will cancel out with this one, and we obtain now the expression of this, well, digital control that is coming from this second Ragazzini design. K is given by this expression over here, and gamma 1 is given by this expression. If you go and look at the first design, you will see that this is a design that corresponds to a particular value of alpha. Remember that alpha was a degree of freedom. Well, if you choose it this way, you will see that in the previous design, this one will cancel out with this one, and you obtain this expression of the controller. And this second controller will not compensate the zeros of the process, of course, because you have left them in the desired transfer function. This is the Matlab code to implement the second design, and well, the first part up to here is of course the same, and what differs is the construction of this second controller. Okay, so you can recognize here the numerator and denominator of this second design. Once you have this second Ragazzini design, you can compute the two relevant transfer functions and have a look at the step responses. Again, in Matlab you will only have the response at the sampling instance, and you will not see the intersample behavior. For that you have to look in Simulink. Well, this is the output closed loop response. In blue the set point, in cyan the desired closed loop response but in continuous time, right? And here you have the closed loop response with this second Ragazzini design with Ts is equal to 1. And this is what you can see again with Matlab. If you go and have a look with Simulink, you can see the intersample behavior, and this is what you obtain. And this time you can see that everything is okay. The continuous time response, so the intersample behavior, is precisely as expected. Well, if you look at the control energy with this second Ragazzini design, you can see also that things look very different. So you do not have anymore this alternation of signs in the control, and this is a well-behaved controller output. So as a conclusion, this method of Ragazzini is really simple to implement. You choose a reference model or a desired closed loop transfer function, and on the basis of the process you can, and this of course desired transfer function, you can compute the controller. The only thing that you have to think of is that there are constraints as far as the causality of the controller is concerned, right? You have to prevent unstable pole zero cancellations, and you have to make sure that this desired transfer function has a unit static gain. We have also seen that it is very important to ensure that you do not cancel zeros of the process that are located in this region over here, because otherwise you will have, well, alternations and oscillations in the control energy, and this will be associated with hidden oscillations.